What's going on, everyone? In today's video, we're going to be taking a look at lower bounds and upper bounds, how we can use that in word problems and context, as well as what it actually does for us in terms of percentage error analysis, or kind of, given the context of a problem, especially when we're doing like optimization or any kind of manufacturing type of problem, we oftentimes have to consider what our lower bound or upper bound are for volumes, perimeters, areas, things of that nature. So let's go ahead and dive right in. So we call them the left and the right ends sometimes of an interval, and what it does is it's giving us an exact value of a measurement that is going to lie in between a lower and upper bounds. Because sometimes when you are manufacturing tin cans or blankets or something like that, sometimes there's an error in the process, and sometimes things are smaller or less than, and sometimes things are bigger or greater than. And we have to take that into account in order to know what our limitations are, what kind of boundaries we are operating within. So let's take a look right here where we have someone named Jane, and her weight is 68 kilograms, and that's to the nearest kilogram. So let's go ahead and determine what the upper and lower bounds of the weight are. So if we think about it, this is to the nearest kilogram, so we're rounding to the nearest whole kilogram. So if we go below 68, what is the smallest value when we round to the nearest kilogram is going to bump up to 68, and that answer is 67.5. Because if it was 67.4, the nearest whole kilogram would be 67. 67.5 is going to round up to 68. So that's going to give us the weight. I'll call that W. And then what would our biggest bound be on the upper side? Well, we can go all the way up to 68.5. And you might notice that 68.5 would round to 69, which means that I actually have to take my little eraser here and erase that or equals to sign. Because as long as it's below 68.5, it's going to round down to 68. So this right here is the inequality notation for our upper and lower bound given the problem. So now let's say that we're taking someone's height, 155, and it's rounded to the nearest centimeter. So what interval are we operating between? So this is the same exact kind of problem where if we're rounding up to 155, the lowest it can be is 154.5, including that value. And then we're going to go all the way up to 155.5, but not including 155.5. Let's take a look at a different example where we have someone who's running 100 meters in 11.3 seconds. Now, Majid's time is going to be measured to the nearest tenth of a second. What are the lower and upper bounds for the running time? So just kind of like how in our last problem where we took the decimal place to the right into consideration, we're going to do the same thing here. So if we're looking at the tenth, we're going to be thinking about the hundredth. Now, if we're rounding to 11.3, what value is going to give us 11.3 when we round to it? What's the smallest one? Well, just like our last one, we're going to look at 11.25. We're going to take into account the decimal place to the right and then see what the smallest value is. Because if I did 11.25 and rounded it to the nearest tenth, that's going to give me 11.3. So I can include this. That would be my time. And I'm going to go all the way up to 11.35, but not including 11.35. Because again, as long as it's below that, it'll round to 11.3, given the context of the problem. So another quick example, let's say that we have a rectangular plot, and it's measured as 172 by 64 meters. Let's determine the lower and upper bounds of its perimeter. So here's the thing, is that what we're given is a rectangle. That's not a rectangle, that's a weird polygon. I don't know why I did that. There we go. 172 by 64. So let's determine the lower and upper bounds. Now, the smallest that these dimensions can be is going to be 63.5 and 171.5, because that's going to round those up. And then the largest they can be is going to be 64.5 as well as 172.5, remembering that it does have to be less than those values, not equal to those values. So if we are going to take the smallest into consideration, well, if I have 63.5, 171.5, and I'm finding the perimeter, if I just use my perimeter, the equation, I would get 470. And then what would I go up to? Well, if I would take 64.5 as one of my lengths, 172.5 as one of my lengths, I'm going to get all the way up to 474. So those are the perimeter boundaries that I would be operating within. All right, so let's take a look at a little bit more difficult problem where we're given that the radius of a cylindrical drum is about 11.2 centimeters and the height is measured to be 35.7 centimeters. Both of these are correct to that one decimal place. And what we want to do is find the upper and lower bounds of the volume of this thing. in order to, see what kind of boundaries we're setting for the manufacturing and production process. And let's round this to the nearest integer. So I know that my volume is going to be pi r squared h for this. If you didn't know, now you know. So again, it helps to state what the minimum is. So again, if 11.2 is going to be let me go ahead and label the radius here. And actually, you know what? Let me go ahead and do max. Let's do a nice table. So my radius here, what's the smallest possible value? So 11.2 is what it's measured to be. But if I go to the decimal place to the right, and I think about what the smallest value of that could be in order to round up to 11.2, it would be 11.15. And what would be the maximum? 11.25. Remember, it goes up to that, but does not include that. And then how about my height? 35.7 is my height. So that means my lowest possible value would be 35.65. And what would be my highest value? It would be 35.75, but again, not including that. So all we have to do is all we have to do is plug these values into here in our calculator, and then plug these values into our calculator here, and we will get our answer. I already went ahead and did that in my calculator, and I found that the minimum possible value is 13,923.8. That would round up, because remember, this is the nearest integer we're talking about. So I would round up to 13,924. For my maximum value, I would have 14,214.5. But remember, this one's a little bit weird because it's our maximum value, so we're actually going to bring that one a little bit down. So what we would say is that we'll have 13,924, and then we're operating that volume into 14,214. Again, a little complicated at first, but if you just follow the steps, look to that decimal place to the right, figure out what your smallest and largest values are, and then plug those into the appropriate formula, that is the blueprint for every type of these problems. Okay, hope that helped, and I'll see you all in the next video.